Yes, so we are live, and we have Manikant Roy and Shawn Ray with us, who are going to be conducting a workshop on data to insights, a case study on data analysis using Python. Right? Uh, Absolutely, the stage is yours, Manikant and Shawn. Yeah?
Okay. Yeah. So I hope I am audible, everyone. Good morning, everyone. I am from Delhi live, and Sean is from the Texas, USA. And we will be presenting this workshop on from data to insight, a case study on data analysis using Python. Okay. And the idea is to give you the exposure how to get started with the data analysis using Python libraries. Right. We'll try our best to give you a 360-degree overview, and by taking a problem statement, and there will be ample of hands-on, right? And you are also free to contact us after the workshop is over in the launch area. So moving onward, the very first thing is that about a methodology. Okay, so what methodology we need to follow, that is really important to understand in data analysis, right? So basically, if you see in business setting, why do we do the data analysis and or data driven things, everything analytics and all that you keep on hearing these days? The idea is to help or improve the business, right? In two aspects. The major aspect is, can we increase the revenue if I look from the finance perspective, or can we reduce the or minimize the risk, right? Maybe for example in preventive maintenance or something like that. So these can be a business objective for which you may do data analysis, right? So if you can see on the left side, there is a whole cycle there. You start understanding the business problem, then you try to apply the analytical approach to that particular business problem. You collect the data, and then once you have understanding of data, you need to prepare data, because in real world data is not very clean and ready to start analyzing, right? So you need to prepare data. We'll talk about that in fact on our hands-on. And then you make some sort of modeling. So we'll talk about what this modeling is all about, and then finally you evaluate your model, and then finally you go for the deployment to solve that particular business problem. Okay, and of course you have a feedback, and then you can see that there is a back loops that involves. Okay, so it's not one time process. You may need to go through the iterative process. So the idea here is, this is the methodology that we need to adopt during data analysis. And the very first thing is that we need to understand what problem we are trying to solve, right? Okay, and once we have a good understanding of the problem, then only we can select our tools and everything in a right manner. So moving onwards, so the idea is to first you have to understand what is my objective. Okay, so for example, if I'm doing data analysis, what I'm trying to solve, what kind of problem I'm trying to solve, what is my objective of that particular problem, that need to be very well defined. Okay, in the beginning. Moving onwards, once you have defined your objective, then you should have a supporting goal, right? Okay, so for example, you should have a team. For example, let's say if you are a data analyst, right, you need to know from where to get the data, what is the domain. For example, you are solving a business problem in marketing, but you may not have a sufficient domain knowledge, right? Okay, of the marketing. So probably you can ask for someone in your organization who can help you with domain knowledge, and in that way you can take the problem. Moving forward, so the once we have defined the goal and we have the objective, right, then we are good to go with the further process, right? Okay, so you have to very much review both the process, like you are not increasing cost while defining the goals, right? And also you are to review the process to identify inefficiencies, right? Okay, for example, your problem is worth to solve. That whole idea is your problem is worth to solve with data analysis and all, because it is a costly affair. Then once you have decided, okay, my problem is there. For example, I can give you an example. Okay, let's say if I have a marketing company and I have a 3 channels: in-person sales, email marketing, and call. Which one is doing better? Let's say I'm trying to understand this problem and trying to solve this problem through my data that I have over the years accumulated, right? So this is a problem that I want to know, which is the most effective channel for us for sales, right? So then once you have defined your problem, you understood your problem, then what is the best analytical approach we have? We need to select. So again, it depends a lot into the according to the problem statement, according to the data that we have, according to the kind of output we are expecting, and so on and so forth. So there is not one thing that I can tell you, okay, this is the best method, right? So basically we need to understand the context, we need to understand the problem, and then we can go ahead. So some of the things that you can use for picking the analytical approach is that, for example, if the question you are trying to solve is to determining probability of an action, okay, using a predictive model. So for example, if I just imagine, for example, if I have bought something, what is likely that I bought something next, okay, or if I have got 6 CGPA in this semester, how much CGP we are expecting I can get in next semester, something like that. In that case, probably you can use predictive model, right, where you are trying to have a probability of an action of the in future. Similarly, if you want to show some kind of relationship, right, then probably you need to go with a descriptive model. And if your question simply requires yes or no answer, probably you can go with a classification model. For example, whether that customer will churn out, will stay with us, right? So this is a simply yes no binary kind of answer. Or I mean, maybe there can be multiple uh, classification problem, multi-class problem. Then you can use classification model. So the idea is all depends on the business requirement, the kind of business requirement you have, okay, according to for the your analytical approach. So you need to really understand your business requirement for selecting model. So you might have seen these days a lot, like a lot of machine learning, deep learning. You might have keep on hearing these jargons, right? So you need to understand, okay, there's a bunch of thing in my as a tool available, or as a technique available, or as algorithms available, which one is suiting according to my problem, right? So if you think that this can be done without machine learning, please do not use machine learning, right? Okay, but if you think that you need to use machine learning, then please go ahead. So that's the idea about it. Okay, so basically what's machine learning? Very simple. You get output without explicitly programmed. Okay, maybe I can show you some demos in the end. So for example, you can see a decision tree, right? So this is one of the model selection where somebody we want to predict outcome of particular event. For example, whether I can play a match today, right? Whether, for example, whether it is cloudy or sunny. So in that case, we can use decision tree to know the output, right? Okay, to know how the day is. Okay, so this is used in real world. And then coming to the next part, once you have defined your problem, you know what analytical approach you are going to use. Then the next step is data, because everything what you're going to do on is data. That's data requirement and data collection, right? So what may happen that you need to collect data from, so there's a lot of brainstorming you need to do. How much data you need, from where you will get, how to get it, right? And what will be my source of data? Okay, so that all you need to think of it, right? So once you have your data in place, and with considering all these factors, right, then you are good to go for the understanding the data. Okay, so preparation of the data. So as I said earlier, data may not be clean in the real world. Okay, so you need to clean the data. What is the meaning of data? For example, you might have missing values, you might have not data in proper unit. For example, they might be in different unit. Just take a simple example. I and Shawn are collaborating. I'm from India and Shawn is collaborating from the US. So Shawn is having different date and time zone, and I'm having different time and zone. Time zone. Imagine if you have a customer from a global, global countries, right? Okay, across the globe. So you might have different dates, different time zones. So before start analysis, you need to put everything in one place. That is what data preparation means. You may have data in different scales, low scale, large scale. So you need to normalize the data. So whole lot of things goes into in data preparation before you start do any kind of some serious analysis on it, right? Okay, so we'll talk about even that in hands-on session moving forward. So then once you have data prepared, then you need to understand the data. Okay, so I will not go into these jargons. Do not worry about these mathematical jargons, okay, as this track is for beginners. So what the point I'm trying to understand here, make you here, is like what kind of data I have, whether I have a categorical data, whether I have numerical data, whether I have a time series data, and so on and so forth. So you will spend enough amount of time for understanding the data. Okay, what is the maximum value, what is the minimum value, right, and so on and so forth. What is my independent variable, dependent variable? So much things you will do while you are trying to understand the data. And there are a lot of things, tools are available which will show you hands-on how you can understand and then take it forward. Okay, of course you can use some sort of visualization, some descriptive statistics you can use to understand your data and have good understanding it. Then again, as we already said about it, during the data preparation, like data quality is very very important, right? And your whole analysis usefulness depends on data quality. If my data is not good, if my data is misleading, right, or there is a inconsistency, then we cannot have a good analysis, right? So data quality does matter. Now then come to the modeling part that already we discussed, right? So it depends on the business requirement whether we need to go with the descriptive analytics or whether we need to go to the predictive analytics. Okay, so again, if you are applying machine learning, probably you need to divide your data in training set and test set. Okay, and then you can make your model and you can test your model. These are the just for the sake of setting the context. Now again, coming back to the understanding the question, that is again we are emphasizing very important to understand, right? Okay, what question you are trying to solve. Okay, because it happens, let's say if you have not understood the question, right? Okay, and then you got some analysis which may not be useful to your organization, right? So your analysis must be very valuable, and it should add some value to the business problem or to the in the growth of organization. Okay, so finally comes to the next part, that is once you have done modeling, then there is evaluation also, right? So as we do in traditional software development, we do test, right? Okay, you remember waterfall model. Okay, so communication, planning, development, and then coding and testing. So testing here when we say in data analysis model, we'll talk about what this model is all about. Okay, then we need to evaluate our model also, right? Okay, how it is doing, on the data, real world data. Okay, there are certain metrics available in Python libraries we use for testing the accuracy of the model. Okay, so this is where evaluation come into the picture of the model. And finally it's a deployment, right? So like we do deployments in the normal software development environment, we have to deploy our model so that it can help us in the real world. Okay, and finally, last but not least, once you have got this result after the analysis, right? Okay, then you need to be you need to be able to understand the result and how to use that result. Because why we are trying everything, I mean, why we are doing all this sort of data analysis and all, because we are trying to get some insight, and we are trying to take some decision. Okay, the strategic decision based on analysis, so that we can stay ahead from our competitor. Okay, or we can get an extra edge over the others. Okay, so understanding the result. Okay, so result will be meant for higher people in hierarchy, for example top level management. As a data analyst, probably you, after you have done your analysis, you need to explain your result to your boss, and then you have to tell them what is the significance of this result and how this can be used in any kind of decision making process. So this brings to the end of this setting the context, right? And this hands-on session, we will be using Jupyter Notebook. We have already shared everything. We'll be happy to share again the link of all the data files and to the Jupyter Notebook, and it will be taken by the Shawn. Okay, so in advance, we are also learners. So if you find any bug or any mistake, do forgive us. We will try to correct together. Okay, and Shawn will be taking to the hands-on session. Okay, so the problem statement that we have taken for this workshop is a very good data set, because it has a good amount of complexity, and the problem statement is that we have a data set of automobile data set, and in that we have to predict the car price. So for example, this guy is trying to sell his car, okay, to a dealer, but he doesn't know what should be the right price, and what are the important factors on which car price depends on, right? Okay, and for this we have a data set. Can we answer his question through a data, right, by applying all sorts of techniques that we have available in as a Python library, right? Okay, so the snapshot of data we have taken from the UCI machine learning repository. This is a very good data set for the beginners, and involves all sorts of steps which is a part of data analysis. For example, reading the data, then cleaning the data, then making a model, and so on and so forth. So we will see in the hands-on session how we are going to answer this question through data. Fine, over to you, Shawn.
Okay, thank you for the wonderful introduction, and I'll go ahead and take it from here. So, first things first, is my screen visible?
Yes.
Okay. So for the people who have just installed Jupyter Notebook, you might see an interface looking something like this. The folder names might be difficult. They might be, sorry, not difficult, different, and they might be different in quantity, but overall it's going to look something like this. So the overall interface is pretty simple, and what you want to do is come over here and go to New, and then just click New Folder. And once you do that, it'll seem as though nothing happened. But then if you scroll down, under U, you'll see something called Untitled Folder. And so we always want to be descriptive when we are programming, no matter what we're programming or when we are. So go ahead and click this check mark. and then click rename, and then just go ahead and give it a nice descriptive name of your choice. So I already have that, so I'm going to go ahead and delete that. So now we come here. So I already have all of this uploaded from the GitHub link, which is already provided to you. But if not, then we can take files directly from our local machine without any intervention from Jupyter Notebook. But we always want to make sure that we are making things as simplistic as possible. And in this case, it's not necessary to take it directly from your local machine. So what you can do is just click upload here. And then you should have the files from Jupyter Notebook, something like this. And you just can click one and then shift to the top and then import them all. Okay, so after that, we're going to go ahead and just open 1.1 because that's where we're going to start.
Shawn, sorry to interrupt. So just to clarify, I guess the files that you just showed us are the ones that the people can download from GitHub, right?
Exactly, yes.
Cool, thank you.
So aside from that, as was told earlier, the problem statement is essentially just to figure out what factors have the biggest effect on the car price, or what characteristics are most closely impacting a car price so that somebody can get the best deal on their car. They don't want to overprice it and they don't want to underprice it. They want to have it just right. So let's go ahead and begin. The first thing we have to do is import 3 major libraries. They are NumPy, Pandas, and matplotlib.pyplot. So let's go through each one. First of all, the syntax. For importing any library, we first put the keyword import, then the name of the library, then as, and then just something that we can use to call it. In this case, for NumPy, we have used NP because that is most commonly used for NumPy, but in theory, you could put anything you want and it would work fine. Now, NumPy is more of the mathematical, scientific, computational side. It deals mainly with your equations and your math and that kind of thing because it is more of just there to support the other libraries in those operations. And then Pandas is your data structure library. It specializes in taking data and making it better, just reforming it and turning it into something that is better for the other libraries to use. And then there's matplotlib.pyplot. So matplotlib.pyplot is different from matplotlib, and we will talk about that later. But for now, all you have to know is that matplotlib.pyplot specializes with visualization. It's best at taking raw data and putting it into something so simple that even someone who hasn't seen the data before can pretty easily understand what the data is trying to represent. So, of course, we have already provided the data set to you. That is knowledge that you already have. So now the first thing we have to do is import the data file. Obviously, we cannot edit or change a data file if we don't have it. So the syntax is, because this is a .csv file or a comma-separated values file, we have to use .readcsv. So this df is just a variable. Now, it stands for data frame, but you can use whatever you want as the variable here. Now, that equals, and then, of course, we're trying to use pandas here to read it. So we're doing pd dot and then read csv. And if you look back here, our file is called auto1.csv. And because of that, we're going to, within quotes, which can be single or double, we put auto1.csv. And now there is header mismatch, which means that not all the headers are properly made. So for that, we can just put a comma and then put header equals none, because we don't want any headers right now because they are not accurate. Okay. Now this, for example, is just how you would export a file. It's pretty similar, but we don't use an equal sign. We use a dot. So we'll put the name of that variable. In this case, it's df. It might be different, but we're using df and then .to.csv. So this is exporting it to a .csv file, and then we just specify a local path. Okay, and then now if we just put df, then normally you wouldn't expect anything to come. In a .py file, it's unlikely you'd get much. But because this is a IPython file, we don't have to use a print statement to get anything from df. We can simply put df and get a nice and neat data frame. Now, the first thing you're probably going to notice is that the headers are simply 1, 0, 1, 2, 3, 4, etc. And that is not descriptive. So we're going to change that later on. But for now, let's move on. Now, there is something called .head. So you're going to take your variable and then put a dot and then a head at the end. Now, if you just leave it as is, like if you just put it like this, it's going to by default show the first 5 rows. So as you can see here, I got 0, 1, 2, 3, and 4, which combined is 5 rows. Now, you can optionally put a number here. So for example, right here, we've put df.head 25. This means that we're going to get the first 25 rows. An additional thing to remember is that we cannot put infinite rows and infinite columns. And if we put a number too large, like say 100, it's still going to have these dots. And so make sure that you are putting a number that is small enough to be within reason. Okay, now df.tail is basically the negative equivalent of df.head. It does the same thing, but instead of taking it from the top, it takes it from the bottom. So if you do not put anything between the parentheses, just like df.head, we get the bottom 5. Now, if we put a large number, again, all these same rules apply, so I'm just going to go beyond that. Okay, now, the first thing that I want to point out here is that when we're doing, say, df.columns, we don't have to use parentheses because we're not actively doing a function. This is merely a statement. Now, when we do df.columns, we get an index of all of the names of the columns. Now, these are integers because at the very beginning, we took out all the names for columns right here. Sorry, the headers. And so we just get numerical numbers. And again, it's quite nonsense and doesn't give us much information. But the next thing we have is df.dtypes. Now, dtypes gives you a list of all of the columns.
Shawn, can you increase the font size, please? Yeah. Okay.
Yeah.
Can you zoom it?
Just a little bit would be good. Yeah.
Okay,
Thanks.
go ahead.
Okay, and then, so df.dtypes, as I was saying, is just going to give you a list of your columns, and beside it, it's going to give you the type. So we know that column 0 is going to be in 64, 1 is a string, 2 is a string. Oh, and by the way, remember that an object is a string. It just says that differently in IPython. And int64 is just an integer, and a float64 is just a float. So just that is definitely something that's notable. Okay. Moving forward, we have df.info. Now, df.info looks pretty complex at first, but it's really not. What we're really just getting here is a non-data frame version of our regular data frame. So you can see we still have a similar interface to our data frame. Like we have 0, 3, 3, 1. We get a similar thing here with 3, 3, 1. So it's basically just a more of a series-oriented way of getting some parts of your data frame. Okay, then we have df.index. It's once again, it's not a function, so we don't have to use the parentheses. And this is talking about your rows. If nothing is specified, it's talking about your rows. So our rows go 0, 1, 2, 3, 4, etc., etc. And that is going to be a 1-step because we're not moving multiple numbers. So if it was like a 2-step, that would mean that we're going 0, 2, 4, 6, and more. So because we are going directly from one number to another, is going to be step equals 1. And the start and stop are pretty self-explanatory. The start is the first row name, and then the stop is the final row's name. Not the name, but rather the position of it oriented with the others. Okay, and then as I was saying earlier, we did take out all of the headers. And so that is not descriptive, and we need the headers. So this is a list of all of the proper header names. And a list is pretty simple. All we have to do is put whatever values we want inside the list within quotes, and then a comma, and then another one. And all of this is going to be within square brackets. Now, we're assigning this the variable headers because that is very self-explanatory, and that is our goal when we are trying to make variables. If we put type headers, we get list as expected. And then at this point, we have made our headers, but we haven't inserted it. So with df.columns equals headers, we're telling pandas to take the columns and then remove them and put the list of headers that we've put in its place. So when we do that, pandas immediately goes and it replaces the current header names with the ones that we have put in the list. Now, if there is a mismatch, so for example, if there is 27 columns total, and in your list of headers, there's only 25, that is going to make a value error, and it is not going to be a successful operation. So it is definitely worth noting that you have to make sure that you have the same amount of values as your columns. So we can do df, and then we can, if we do df.info again, and we put it, this time note how we've put parentheses. When we put parentheses, we get this, more of this kind of interface. If you remember from earlier, we got more of a series type data frame, which is basically just a data frame, but in a series format. And that's not going to be too helpful because we already have the regular data frame. So with the parentheses, we get a list, which is very nicely organized with the number of the column name, the non-null count, and the D type. The D type, as I talked about earlier, is just the type. So whether it's a string, a float, an integer, etc. But the non-null count is basically just all the values that are there. This is talking about whether or not there's any missing values. So it does say non-null everywhere, which means that we should be pretty good assuming that those are correct, which they normally will be. Now, this is just another D type, so we can move on. Okay, now we're at df.describe. When we do df.describe and just parentheses with nothing else, we by default only get the numerical data columns. So we do have, so you can see that there's a lot fewer columns here than we saw in the earlier data frame. And that's because we did not specify anything. So by default, pandas is only going to show the numerical columns. And you can see that these operations are count, and then mean or average, standard deviation, the minimum, these three are interquartile range, and then the maximum. So the count for all of them is 205 because they have all the rows, because they all have 205 rows. And moving on, if we do include all in the parentheses, then it's going to take everything. That's going to bring in the categorical data and the numerical data. Now, obviously, we cannot run an operation like minimum or maximum on categorical data. And so because of that, we do not run those operations, in fact. You can see that we now have 3 new operations, which is unique, top, and frequency. So the count is going to be the same for the most part because we can see that they are the same, in fact, in a different way because these are integers and these are floats. But nonetheless, the count is going to be the same. And then we have unique. Unique is going to be used on only categorical data. So we can see how many unique values there are within a given column. Then we have top. The top is self-explanatory. It's just talking about what's at the top. Then there's frequency. Frequency just talks about how many times something occurs. So we can see that it's not applied to the numerical data, but the categorical data all have a frequency. And then we have our numerical data, and you can see that if it is a mismatch of types, like for example, we cannot run frequency on the numerical data, so it just shows nan. Same here. That's why we have this big patch of nan here. Okay. So yeah, moving on, we have dropna. So dropna we can use to take away a row or a column. So in this case, we're taking the subset price, and because because we're talking about access equals 0, this means that rather than taking away a column, we're taking away a row. If this was access equals 1, that would mean we're trying to take away a column. There are only 2 positions for the axis, 0 or 1. 0 is row and 1 is column. So you can see now that we have lost a row. It's now 205 rows. And moving on, we can do df.head. And these are the 2 other ways we can, okay, let's look at this list, in fact. So these, we have a lot of formats that we can use. We have the CSV, of course, and then we have JSON, which is JavaScript. Then we have Excel, which will bring in XLSX format, HDF, and then SQL. So you can use all of them. And for reading, you're going to use pd.read and then an underscore and then whatever data format you're using. For save, you're going to do df dot or whatever your variable is. In this case, df, but whatever you use, that dot and then 2 underscore, whatever your data format is. Okay, so that brings us to an end of this notebook. So let's talk about our key learnings. In the beginning, we talked about how we could read our data. We talked about how we could use pd.read, and then we could read any format of data from this list. Then we talked about organizing the data. As you remember, at the very beginning, we took away all of the headers because they were not properly organized. Then after that, we talked about how we could get an overview of the data. We talked about the head, the tail, .info, .dtypes, and the index. And these are, of course, not too advanced. They are just giving you an overview of your data and letting you get an idea of what your data is about. Then the summary statistics are just basic insights. And as you remember, the summary statistics were just about different operations run on your data and the output of that. And that does help to get an idea on what your data is about, again, just like all of the other operations. So at this point, you can go ahead and close the 1.1. And now we're going to move on to 1.2. So you can go ahead and click 1.2.
Shawn, meanwhile, if there is any question that we can take. Yeah.
Oh, yes. If there's any questions.
Yeah.
If there's any questions, then that can be taken.
Or you can write in chat box. We are there to answer that.
Yeah. Okay. So now we are going to begin our 1.2 notebook, as I talked about earlier. So the first step should always be to import your three libraries, pandas, numpy, and matplotlib.pyplot. I will say that you should probably always import these libraries together, regardless of whether you think you'll need them or not, because they're just so popular, so useful, and so commonly used. So that's that. And then the next step is very similar to previously. We read our data, so we're going to read our data again in a very similar format. We're going to remove our headers because remember that when you are performing an operation onto your data file, until you export the file, you're not actually making any changes onto the original data file. So you have to export this if you want to see your changes, because otherwise you're going to, if you download this at the, like say, since we're dealing with auto 1 year, if we just click this and click download, we would still get the original data file because this is not actually editing the original file interactively. So you read your file. This is just df to make sure that we have everything properly. This is just a continuation of that. We can perform df head, df tail. And then we have to add our headers back as we did last time. Now we have our headers in proper position. Okay. So when you are looking at the data, you can already see multiple nans, such as here, 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 and here. So we definitely want to reduce any missing values as much as we possibly can. Missing values are really bad. They mess up our data, they corrupt our data, and they can prevent doing operations that are really necessary. So to do that,
Shawn, can you little zoom? Okay. Yeah, and just go a little bit slow. Yeah, sure, little bit. That's it. Please go ahead.
So this shows nan, but before we perform this operation, you can see that they were actually question marks. So what NumPy is doing here is replacing the question marks with nan, because nan is how a computer knows that there is a missing value, and it is the preferred way of expressing a missing value. So it's a very simple syntax where we just do df.replace, and then we do whatever we need to replace, in this case a question mark. Then we perform our np.nan, and then in place, we always want to make sure that is true. Okay, and we can do df again just to make sure that our nans are correctly done. Okay. Notice that if we use the print df rather than simply df, we do get a different interface. We're not getting the same, clean table type interface. We're rather getting a series-oriented interface again. And so you do definitely have to remember that these will give you different interfaces, and you have to think about and properly choose which one is preferable for you at the given time with the given data.
So I have a question.
Okay.
So you replaced the question marks, which was basically junk data points, with nan, right?
Correct. Yes.
So so replacing those data points with nan would that be helpful when I'm doing operations for that particular data cell? Would that
Certainly, because
legal falsely value?
Yeah, certainly, because what NAN does is it's commonly recognized across platforms, across languages, and across servers as a signal for a missing value. If it comes across a question mark, or say, a crazy outrageous number, like if we had 9999, and then it might think that that is actually part of the data and perform an operation including that. So we want to make sure that we have NAN, because that way it knows to either skip it or throw an error.
Got you. Thanks.
No problem. Okay, so continuing on, we can go to the next. Okay, so we can do df.head2 to make sure, we want to make sure that our operations are successful, because it's very, very bad if we do an operation and we realize later on that it wasn't successful. So make sure you do several tests to make sure that your operation has been completed successfully. Okay, so there are D types. Okay. Now, here we start talking about .as type. So we're going to take an average now, and we're even going as far as assigning it to a variable. Our variable in this case is going to be called average1. So we're taking the column normalized losses, which is this one, and we're making it a float, and then taking the mean of it. Now, here's what you have to notice here. If we go back to our D types, normalized losses is an object. Even though it clearly has numbers, it is classified as an object. The reason for this is that Python can recognize numbers as strings. If you put a number within quotes, Python will recognize it as a string. So you have to be very careful to make sure that data mismatch is not too severe in whatever you're doing. So here, what we do is we use as type float, which means we are telling Python disregard whatever it thought that the type of the data was, and we're telling it make this data a float regardless of what you think it is. So now it has been turned into a float, and that means we can conduct the mean operation, and of course access equals 0 because we're performing the action on the row, not the column. So we get 122, which makes sense given we have numbers like 164 and 95. Okay. Now we can, this is when you start to see how useful these things can be. So we can do this now that we have an average. Of course, we cannot be 100% sure that the missing value is going to be exactly the same as the average. Matter of fact, it's highly unlikely that it'll be the exact same thing as the average. But it is going to be it'll be a much more accurate choice than choosing like just, something from the air, like 9,999. That's obviously just random. So with our average, we can make sure that our data is as close to what it would have been as possible. So what we do is we take our replace command, and we've used this a couple of times, and we can use it a lot. And you can see here now why NaN is so helpful. We can simply put np.nan instead of having to perform fancy operations and potentially messing up our data. So now it can take the NaN and replace them with the average. So now you can see that let's take let's take these first three values, for example. We have one NaN here, one NaN here, and one NaN here. Below, though, once we've performed our operation, you can see that all of them have been replaced with our average, which is 122, which thereby makes our data cleaner and more readable, as well as potentially more accurate than simply something random. So now we can also perform an action called df.mean. So when we do df.mean as a function, what it does is it just takes all of our columns, which are numerical data, and it takes the averages of them and it puts it before you. So here you can see that it has taken all of our numerical data and simply performed average operation on it and given us all of the averages of all of the columns.
Sorry for interrupting. There seems to be a question from one of your attendees, Sweetlin, and she's asked it in the SciPy chat. And she asks, what if the question mark or the junk data appears in the middle of the data set and can't be found at the head or the tail? How to identify that?
Okay, in that case, it is a little bit more complicated. So If it does appear in the middle of the data, that means that you're going to have to perform special operations. So our standard head or tail is not going to do too much. So I'm assuming what you're asking is, what if I don't know that the question mark is there? So the best way to do that is to actually access the data file itself. Like, for example, we can open this data file like this. And
Sean, just a minute. Of course, sorry to interrupt, but we have some functions like is null, not null kind of function, which can give you, idea about whether you have missing values or not without looking explicitly each rows, right? So no matter we have thousands or whatever, right? We have some functions. I think Sean is going to do that in further. Yeah. Is it
yeah,
right, Sean?
we'll do that further in.
Perfect.
Thank you.
So the is null not null again is basically just to identify special characters, and it is definitely the best automated way to do it. So if that's what you're talking about, then yes, that's the best. Okay, so let's go ahead and find where we were. Okay, right here, the mean. So as we talked about, it takes all of the means for all of the columns and presents them before you, for all the numerical columns. Okay, performing details. Now, what we're doing here is just continuing our operations with making sure that we have as little nans and missing values as possible. So for average 2, we want to make sure that it is classified as a float and not something like a string or something else, like date times 64. So we're just trying to make sure that it is a numerical data so we can perform our operations simply. So we do that. Then we can replace our data with the average like we did last time. And now we might not be able to see it necessarily, but we can definitely know that it has been replaced. And in fact, if we put a new column right underneath this and just call for our average 2, it is 3.329. So if we look, we can hopefully find somewhere where it has been used. Let's see, 3.32. So let's try using df.head in this case.
So sorry again, and Sweetlin seems to be asking, is this not the mean of a column? And how is it the mean of a row? I think she meant something in the past few cells, your context. You could maybe just show it to her or show it on the screen again.
Wait, the average?
The mean of a column. Yes, I think so. That.
Yes. So this is, well, it is, no, what I mean is that it's taking the row of it, it's taking the mean of an entire column. So for example, for symboling, it's taking the average of every single data here, every single piece of data here. So it's taking 3, 3, 1, 2, and everything in between, and taking the average of that and presenting.
Right.
So we do our DF2, and we do a couple of averages here. So I'm just going to skip past that because they're all pretty synonymous, and we're just trying to replace missing data with averages. Okay. And then, so as we were talking about with is null and not null, we can use is null and not null to see whether our data is missing or not. Now, if it's true, that means that we have missing data, and we need to make sure that that is perfected. If it's not, if it says false, that means that we're good and we can proceed. So we've put is null, and we can see that all of them are false, and that means that we should be good. Okay. Now we're talking about a new thing called value counts. So to see what values are present in a column, we can use value counts. This is basically just showing you the frequency again. So it's showing you how many times something appears. So for a number of doors, for example, which is an object, so categorical data, we can see that there's 2 and 4. So we can expect that there's mainly just going to be 4 and 2 as our data. And we can see, in fact, here that the only different types of data are 4 and 2, since you would imagine that a car would either have 4 doors or 2 doors. So we also see that there are 114 instances of a 4-door car and 89 instances of a 2-door car. So again, like I was talking about earlier, we're always gonna use the higher frequency data okay, so it's actually a little bit different from the numerical data, but it's very similar. Just the way that in numerical data, we're using our average to replace the missing data, when we're talking about categorical data, we're gonna use our highest frequency one because that has the highest likelihood of being correct because it's gonna be it's most likely, it's not necessarily going to be correct, but it's most likely to be correct because it appears more in the data we already have present. So IDX max is basically just value counts, but it shows you the most frequent data type instead of just the numbers. So if we run IDX max on any given column here, for example, we're running it on the number of doors, we can see that it is 4, and we can even confirm that because it does indeed have more than 2. Okay, and then it's a very similar operation for the most part to replace the categorical data's missing values. So here we're just using the dot replace again np.nan because that makes it so simple, and we're replacing every instance of where it says nan with 4. And so now everywhere where we previously had missing data has now been replaced by 4. Okay, and now we can confirm by using isNull that all of our data is going to be false, which means that there is not missing data. Okay, we can run a few more operations. In this case, because, okay, as I was speaking of earlier, we are not editing the original file. So if you are moving from one notebook to another, you either have to export the file at the very end, or you have to do all the operations again. So if you remember in 1.1, we also dropped that other row, and we have to do the same action here because it is not editing the original file, and it would be different otherwise. So we do that. We're resetting our index so that it re-indexes everything and makes sure that the operation has been counted. And of course, we want drop to be true. That way our column is dropped. Sorry, our row is dropped. And yeah, and now we can see that let me go to okay, let's go ahead and make a DF so we can confirm. Okay, we can see we now have 201 rows, which means we have had plenty of reductions from when we have removed rows in the past. Okay, so again, mismatch of data types, we always want to make sure that our data is being accurately represented with as for the data type. So for replacing the correct type of data, we have to do this manually. So we have to manually look at the columns and figure out whether they are in fact a numerical data or a categorical data. And so we use our df, we put whatever columns we need, and then we use .asType like we used earlier to replace the data type with the correct one. And then it says done just because we added this print statement, so we knew the operation was completed. Okay, and let's confirm why we have this there. Okay, so we now know that we have more missing data. So you can see that the error says cannot convert float nan to integer. That means that we do have to go back and double check to see whether or not we have missing data. So that's something that we definitely are going to do afterwards. So moving on, we can confirm that our D types are correct. And because you can see that they are all changed to the proper type now. Okay, if you do df.info with parentheses, it's going to show you a similar thing. And now you can see that they are all non-null, which is definitely what you want. Okay, more df.d. Okay, so now we're going to be talking about data standardization. So let's look at this example. City name. There's a lot of names for something like New York City. Some people might call it simply New York City. Some might call it New York. Some might call it New York Harbor. Some might call it the Big Apple. Some might call it NYC. Some might call it NY, etc. So we have to make sure that they are all of those same data, which are called by different names, are combined. So standardization is the process of transforming data into a common format, which allows the person to make a meaningful comparison. So for example, we're going to now make a new column. That column is going to help us combine, or rather standardize, our data. So for example, here in the United States, we normally use mpg, or miles per gallon. But in India, I'm pretty sure that most people are going to use liters per kilometer. And so we do want to make sure that those are not counted separately and as different data, because they're the same data, they're just by different names. So so this is a mathematical operation because we're dividing 235 by the city mpg, because we know that by knowledge, we know that that's the operation you have to do to convert the miles per gallon to the liters per 100 kilometers. So we create the column like this, as if it was a regular column. We put an equal sign, and then we put the operation we want to perform on the current column. So this is our df.head, and we can now see here we have a brand new column called city and liters per 100 kilometers, and it has all of our new data. Okay. So now what we appear to be doing here is first of all, we're taking our df.head, then we're renaming the columns highway mpg to highway liters per 100 kilometers. And then again, we always want to make sure that we're doing in place equals true, because it is never a good idea, because if we put false, then that would mean that we're not trying to affect that data. And then that can not only cause problems, but also corruption and, of course, mismatch. Okay, so after standardization, we want to perform normalization. So normalization is transforming several variables that are in several ranges to a similar range. So typical normalizations with the scaling, the variable average is 0. So scaling the variable, so the variable variance is 1, or scaling variable, so the variable values range from 0 to 1. So the way we're going to demonstrate this is saying that we want to scale length, width, and height. So we want to make sure that those values are normalized, so their values are from 0 to 1. So our approach is going to be to replace the original value by the original value over the maximum value. So original value over maximum value is the approach that we're going to take. So we do df.dtypes. Again, we always want to be constantly doing this to make sure that our data is not getting messed up. Okay, so we are going to replace the original value so we're going to do original value over maximum value, as we talked about earlier. And once we do that, we can perform .max. And then if we do .head10, that's going to show us our first 10 rows. And you can indeed see that they are now all in the range of 0 to 1. And that is the point of normalization, to get it within that similar range to make sure that everything is not too different. So binning. Binning is just taking a lot of continuous, or rather not taking a lot of, but transforming those continuous numerical variables into what we call bins. They're just discrete categorical bins. And this is going to allow us to do better grouped analysis. So example, in our data set, horsepower is a real valued variable ranging from 48 to 288. And it has 57 unique values, as we can see if we performed an operation such as df dot summary statistics. And then what if we only care about the price difference between cars with high horsepower, medium horsepower, and little horsepower? So what we're basically doing is making ranges here. Rather than having, 20, 30, 50, 60 in different values, we want to just get one thing. It's either going to be low, medium, or high. And so we can use the pandas cut method to put it into 3 bins. So first of all, we want to make sure that there's no mismatch. So we're doing as type float and copy equals true. Remember that equals true means that we want to make sure that that operation is confirmed and proceeded to be done. Okay, bin width equal. Okay, so in this case, what we're basically doing is some mathematical operations in order to make sure that our bins are completed. So we make our bin width, and then now we're going to use NumPy. So NumPy.arrange is basically allowing us to arrange. So NumPy.arrange is a NumPy feature, of course, because we're using NP dot, and that's allowing us to perform mathematical operations to to actually make those bins and put the proper values in the proper bins. So remember, like I said in the beginning, you're going to be using NumPy for most of your major mathematical operations. So we get an array, 48, 101.5, 155, and this is really not too much of a value that you want to care about, because we're now going to see why. We're now going to really confirm that this has actually happened. So now we have to make group names because the mathematical operation is complete, but we haven't given the names yet. So our names are going to be low, medium, and high. And then now we're making our column. So we're using the df horsepower bin, and we're using the pandas method cut. And this is a lot of stuff, but it's really simple. We're just putting it into bins. Our label called group names, and then include the lowest is going to be true because, again, we want to include as much as we can. We need to include it. So df, okay, so this is the same thing again. This is just telling us to show the head of these two. And oh, one more thing. For these square brackets, one square bracket pair means that you only want to show a series. If you use two square brackets, like we have here, that means you intend to show a data frame. And that's very important because if we only used one, it would show us a series. And now you can see that all of these have been conveniently arranged into medium, low, and high, depending on their value. Okay, let's proceed. Okay, now we're going to start visualizing a little bit, because as soon as you start to see that we're using Matplotlib, that should turn a gear in your brain that we're now going to start visualizing, because Matplotlib is going to be used primarily for visualization. So in this case, what we're trying to visualize are our bins. So this process is more or less pretty self-explanatory. So the first thing we have to do is create our A. That should be 0, 1, 2 for the majority of the times that you're going to make a Matplotlib graph. You're going to be using 0, 1, and 2, of course, unless your data is of massive size. So now we want to draw the histogram. And because we have 3 bins, medium, low, and high, we want to put bins equals 3. That way it knows to create 3 bins. Okay, then we set our XY labels and plot title. So that's just going to be pretty self-explanatory again. Horsepower is down here, count is here, and horsepower bins is here. Okay, this is just going to be on a lot of different things. So you can see we've done it on price bins and on horsepower bins. Okay, let's talk about indicator variables. Indicator variables, also called dummy variables, are numerical variables used to label categories. They're called dummies because the numbers themselves don't really have any specific meaning, and they're not really going to be a major variable that you're going to be using a lot. So we can use categorical variables for regression analysis in the later module. So for example, here, we can see that our column fuel type has gas and diesel. Now, regression analysis does not recognize words, only numbers. So to use this attribute, we're just going to convert them into indicator variables. So in this case, we're giving diesel the value 0 and gas the value 1. So this is pretty self-explanatory, and it's just turning all of the gas into 1 and all of the diesel types into 0. And now you can see that both of these have been converted into zeros and ones. Okay, so now we want to make sure that df and our dummy variable are merged, because that way we can actually see meaningful changes within our data frame. So pandas has a operation called concat, which is short for concatenate, of course, and that we can concatenate any number of different entities or different variables in this case. So what we are combining is, of course, df and dummy variable 1, because we want to combine our dummy variable with our main data frame. So we just conduct this operation pretty simply by putting pd.concat and then using a comma separator to separate what we want to concatenate, And then remember, notice how this has changed to axis equals 1, because this time we're trying to affect the columns, not the rows. So now we can use df.drop to just take away the original column, which is fuel type, from the data frame. Again, axis equals 1, since this is a column. In place, as always, is true.
Shawn, there seems to be a question, and
Okay.
I think this is with respect to the column data munching that you were just doing before, a few cells before. So Sweetlin asks, is in place equal to true and copy equal to true? Are they the same thing or are they different?
They are more or less the same thing. The in place equals true is to confirm really any operation where you're trying to move something, or like, for example, in place equals true, as we used here. That's just signifying that we're trying to like remove the column. If we use copy equals true, that's only to be used if we are copying something from one place to another. In that case, we would put copy equals true or copy equals false. That's going to be separate, only to be used for copying. Okay. So yeah, let's keep going. So you can see we've done this multiple times. We've used the get dummies with a lot of different columns. We've also, okay, let's talk about this. Here we are doing we're conducting the same operation, but with aspiration. We're doing aspiration STD and aspiration turbo, and of course assigning them zeros and ones. We do this a lot of times, as for here. And now we're going to wrap up this notebook. So reading the data. Okay, pre-processing, this is basically just getting the data ready for higher operations and the normal data processing so that it can get fit. So pre-processing, which is basically just getting ready for real processing. Missing values, of course, using np.nan, we replace any missing values with nan. And of course, we can use is null and not null to know if we have them. Now, data type mismatch is essentially just talking about which values are not correctly interpreted. So as we saw earlier, the library pandas can get a lot of the values wrong. They can think that integers are strings, floats are objects, and so on. So we want to make sure that those are properly fit. Then we talked about data formatting. So formatting is basically just making sure that the data is, well, pretty self-explanatorily properly formatted. So that's just making sure that we have everything in a nice, neat, and ready for processing way. Data normalization, as we talked about earlier, was making sure that all of the data was within a reasonable range. This also goes side with side with data standardization, which is making sure that all of the same types of data are within one group rather than being separate. After that, we also talked about how we could use .as type to convert categorical data to numerical data. Okay, and we also talked about identifier variables or dummy variables, which simply...
Okay, sure. Yeah. Okay,
Yes?
go on.
Okay, at the end, we talked about
please go on.
Dummy variables, which are there just to be used to concatenate or simply there to give a number. So you just use it to get zeros and ones, not to conduct any significant operation. So that's the end of 1.2, and we can go ahead and go to 1.3. Okay, this is exploratory data analysis now. So what we're still trying to figure out, again, is what characteristics have the biggest impact on the car price. So EDA is used to answer questions, test business assumptions, generate hypotheses for further analysis. And along with that, it's also used to prepare it for modeling. Modeling, again, is taking our raw data and putting it into a visual format so people can see it and understand it just by looking at it. So to reach these goals, we can get a basic description of the data in text, for example. We can visualize it using matplotlib, for example. We can identify patterns in it or seeing how data fluctuates with another. And we can identify challenges of using the data, such as lots of missing values, uncertain averages, etc. Okay, so of course, EDA is all about getting to know your data. one of the most important steps to do this is by getting a basic description of your data. A basic description of your data is very
Sean,
broad.
Sean,
It is
Sean, Sean, can you zoom? Can you zoom and go a little slow, please? Thank you.
yeah.
And Sean, sorry to interrupt, but then Sweetlin seems to be asking another doubt, and she
Yeah.
says that this is with respect to the earlier notebook, I guess. And she asks, when there are missing values in the data, why does df.info say not null for all the columns?
Okay. So I'll take this question. When you say a missing value, right, it has got a lot of meaning. If whether there is a blank, right? So when we do df.info, as per our understanding, right? Okay, there's no blank value right there. There's a question mark, right? Okay, but that question mark is not meaningful to our analysis, right, Sean?
right.
I think Sean got disconnected.
No,
I
I'm
hope,
here.
yeah, I hope I was able to put into the perspective. Yeah.
Oh, I think he's dropped off.
No, I'm here. I'm here.
Okay.
Okay, cool. Yeah.
Yeah. Okay. Go ahead. Go ahead. Yeah.
Okay. So remember, we're not editing our actual data, so we have to do all of our previous operations, such as importing our libraries. And another thing is that now we're shifting from the regular auto data to the clean data. So this is a clean version of our data. Okay, so now we can do similar operations like df and df.describe, df.info. Okay, now let's talk about descriptive statistical analysis, or DSA. So the describe function, of course, automatically computes the basic statistics for all of the continuous variables. Now, again, another benefit of using the nans is that they are automatically skipped. If it was a question mark, if we just left it as is and it was a question mark, then it could actually produce an error or, of course, skew the data. This will show the count, the mean, the standard deviation, the minimum value, the interquartile range, and the maximum value, as we talked about earlier. Okay, we're also going to be using Seaborn now, also for visualization, but we're going to be using it alongside Matplotlib. Okay, step 2, we got to analyze individual feature patterns using visualization methods. So the question here is how we're going to choose the right visualization method. So when visualizing individual variables, it's very important to first understand what type of variable you're dealing with. This will help us find the right visualization method for that variable. So we can do operations like dtypes, and okay, this is a new one. This is df.core, which is for correlation. Now, the first thing I want you to notice is that these columns are just duplicated here and here. So you'll see that there's actually diagonal lines of ones because that's going to be where the two equal ones correlate. And so those are always going to be 1 because they're the exact same values. But aside from that, this is definitely going to be a useful chart when you're trying to find correlation between different columns. Okay. For peak RPM and price, we can also get individual correlations like here for peak RPM and price. We still see that diagonal. We can still see the diagonal 1 because they're where they're meeting. They are where they're meeting. Price, and peak RPM. Same thing here with length and price. Okay, question number 2. Find the correlation between the following columns: bore, stroke, compression ratio, and horsepower. So we can also conduct this on more than 2. In this case, we're doing it on bore, stroke, compression ratio, and horsepower. So you can see there's still that diagonal 1, but overall, it gives you all of the, again, this is descriptive statistical analysis. That's giving us a description of our data. We're getting those correlations and understanding how they're correlated. So we can say with certainty that compression ratio and bore are not very well correlated, but then we can also say that horsepower and horsepower are very well correlated, or something like horsepower and bore are more or less pretty well correlated. Okay. Continuous numerical variables. So continuous numerical variables are any variables that contain any value within some range. Continuous numerical variables can have int or float, so integer or floats. A great way to visualize this is with scatter plots and fitted lines. So in order to start understanding this, we can use regplot, so, which is regression plot, of course. Also, how much time do we have left now?
2 minutes. 2 minutes.
2 minutes. Okay. So, regression plot. So, regression plot is a very simple way to visualize
So I guess we have about 50 minutes,
Okay, that's about right.
and then we
Perfect.
have lunch break. So, yeah.
Okay, so we can make a regression plot. In this case, we are doing it with engine size and price. So now we're actually starting to answer the question. Our question was again, which characteristics and which features have the biggest impact on car price? So first of all, this is a very good regression line. We can see that the points are pretty close to that general trend line. So as the engine size goes up, the price is going up too. This is, of course, a positive direct correlation because we want this to be going up. That means that the higher engine size it is, the higher price it is. And we can say that with pretty good certainty given the trend line. Now we can also use the manual core method, and so it's really about whether you're trying to visualize it or whether you're trying to get a basic description. This is visualization, and this is a basic description. So you definitely also want to know, what am I looking for? Am I looking for a visualization method via a chart or a graph, or am I looking for something that is more of just a basic description? So that's what we're getting here. We can also
Son, just a minute, just a minute. I want to chip in here. So I just want to put one point here is that now we have a 26 feature to predict the price of the car, right? Where price is like your dependent variable, which is depending. We are trying to find out what are the features on which this price is depending on, right? And we are trying to find out the important features out of that. So in such kind of analysis, when you have already defined your independent and dependent variable, right, you want to know which is the most important independent variable which can affect your dependent variable. That is why, and in this case it is the price. And you see all other features we have 26 features like body style, number of doors, normalized losses, city liter per kilometer, and so on and so forth, right? So when you start this analysis part, right, before making a model, you try to pick out all the important features only. You will not take all 26 feature into the consideration. And this correlation is where this is when you start calculating this correlation, right? This helps you to identify the best possible predictor for your dependent variable, right? And correlation is just one of the first step that you can take. There are many other things that you can do, but correlation is one to start with. Okay, Shawn, please go ahead.
Yeah, so again, supporting that theory, the price is on the y-axis, which means that it is going to be the independent variable. So this is a very, very strange visualization. You would imagine that a car with better efficiency would be more expensive, but what we can see with this trend line is that the better the car mileage, the less the price, which is absurd. And that is also supported with the basic description via the dot core. We can see that it's -7, which is strong negative correlation. And but another thing to see is that it's not a very good trend line. I mean, the points are not hugging to the trend line very much. And again, here's another thing. This is not necessarily only with the highway MPG. You have to remember that there are a lot of factors that could come into play. Now, here's the thing. If you have a car with barely any mileage at all, chances are it's a big car, it's an expensive car, it's a luxurious car. On the other hand, if you're getting more than 50 miles per gallon, you're probably driving a very small compact car. And so that can really make the price go down. And so that could be a potential solution to this, although we won't know that until we start doing our modeling. Okay, so weak linear relationship. So here is an example of a not so good relationship. We can test peak RPM, and the correlation is next to nothing. We can see that it's very, very close to 0, and the data points are not even close to the trend line for the most part. And so we can be pretty sure that the peak RPM has very little impact on the total price. So yes, as it says here, it's not a good predictor of price because the regression line is close to horizontal. Also, the data points are not very close to the line itself. Again, we can use the df.core to get a table of correlations. Okay, and then another regression plot, we can test the variation between the stroke, and the price. So we can see with this one too that although it's not horrible, it is still not seeming like a good predictor of price because it is very close to horizontal and the data points are scattered. Okay, categorical variables. So these are variables that are describing characteristics, and they are selected from a very small group of categories. The categorical variables can have either the type object or N64. Now, we cannot use regression plots anymore because this is categorical and we no longer have numbers to show. So let's take a look at body style and price. So you can see here that the different distributions of price between the different body style categories have significant overlap, and so body style is likely not going to be a good predictor of price. Let's do the same with engine location and price. So here you can see that they are pretty distinct enough to, so it is distinct enough to say that it is reasonable that engine location is a good predictor of price. And this is also supported by the common knowledge that lots of expensive race cars and supercars, they have their engines in the back. And while that might not affect this, that is again something you have to include in your modeling so that you can properly understand why the data is so, not just why the data is there. Okay. This is on drive wheels and price, and so we want to make sure that we maximize the number of plots we make. That way we can see it with a lot of different variables and, a lot of different columns and a lot of different methods. That way we're not just stuck with one single chart because we cannot make much from it. Okay. We can see that drive wheels is a good predictor of price, potentially, because it does seem to be somewhat distinct. Let's take a look by using a description method. So what this is going to show is our summary statistics. We can use df.describe and we get our chart of descriptions with the count, mean, standard deviation, minimum, our inner quartile range, and maximum. So like we were talking about earlier, the default setting skips objects. So we can apply these manually by putting include object, or optionally, as we did earlier, we can put include all, which will include everything. So only these four statistical analysis or statistical analyses can be done on categorical data. Okay, value counts. So value counts, like we talked about, are good at understanding the frequency. So we can see that we have a large number of forward wheel drives in drive wheels, a somewhat large number of rear wheel drive, and very few four-wheel drives. So we can use the .to frame method to take this series and put it into a data frame. So now we have a data frame which shows us the exact same data but in a data frame. Okay. Now we can save this to a data frame called drive wheels counts. So this is what this is doing is saving the data. So now we have drive wheels counts as a variable that is saved. It's no longer just there. Like here, we didn't save it to a variable. We merely put it in a frame. Now we're saving that. So we can, of course, rename this, and we're renaming this from drive wheels to value counts. Okay, we can also rename the indexing. So we can, in this case, we're changing the index to drive wheels. And this is the same process with engine location. Okay, now let's talk about grouping. The keyword here is going to be the group by method. So the group by method is groups data by different categories. So this is again with categorical data. So the data is grouped based on one or several variables, and analysis is performed on those individual groups. So in this case, we are not doing frequency, but figuring out what our unique different values are. So in drive wheels, we saw with the frequency that we had a lot of forward-wheel drives, quite a few rear-wheel drives, and very few four-wheel drives. And because we only saw those three, we know that we have rear-wheel drive, forward-wheel drives, and rear-wheel drives. So, but that is not enough for the computer. I mean, what if we had 1 million different values? It wouldn't be very easy to enter that, right? So This allows us to put it into an array using pandas. So if we want to know which type of drive wheel is going to be the most valuable, so which one makes the price highest, we can we can group drive wheels and then average them. So we can select drive wheels, body style, and price, and we're assigning this to the variable df group 1. So once we do our group by, and in this case, we want to set our index to false because we're not wanting to do any indexing here. And then we just get the mean. It's that simple. We get the mean, and we can see that the rear wheel drives are not only lowest in quantity, but also most expensive in price. Most popular in quantity and most affecting of price. Of course, we can do D types on any data frame, and so we can also do this on DF group 1. And now we can see that drive wheels are objects or strings, which is correct, and we can see that price is floats, and that is also correct. So of course, from our data, we can assume that rear wheel drives are the most expensive, and fore wheels and front wheels are around the same price. Although we can also say that the four-wheel drives may be a little more expensive, but are around the same price range. Okay, so we can also group with multiple variables. So in this example, we're grouping with drive wheels and body styles. This method is going to group the data frame by the unique combinations drive wheels and body style. We can store these in another variable called group test1. So we do our test to group them. Then we can use group by, again, setting our index to false because we do not want to index it. And then we can use dot mean to get the averages. And now you can see the average pricing. So it's a lot easier to visualize. This group data is a lot easier to visualize when it is made into a pivot table. A pivot table is similar to an Excel spreadsheet, and it has one variable along the column and another along the row. We can convert it to a pivot pretty easily to create a pivot table from the groups. So in this case, we're going to leave the data wheel variable, the drive wheel variable as the rows of the table, and the pivot body style to become the columns of the table. So we're making another variable here called grouped pivot, and we're assigning it the group test1, and then we're using dot pivot. That's going to turn into a pivot table, and so all we have to tell it aside from that is the index, which we're setting to drive wheels, and the columns, which we are setting to body style. Okay, and if we put group pivot, we can see we get these operations. And the NANDs do not signify missing data here. They merely signify that we're not conducting the operation due to some reason. So, here's how we figure out what to do. So in this case, we cannot conduct it because it is not in a legible and reasonable enough type of data to conduct the operation. It doesn't mean that it's missing data. It merely means that it's not a float. So to fill these, we can fill them with 0, but we can use any other value too. It should also be mentioned that missing data is pretty complex, and that can honestly have its own workshop. So grouped pivot, we can use the dot fill not method to fill all of the missing datas with a number. In this case, we're filling it with 0, but we could fill it with anything else we wanted. Okay, and then we are we're making another variable called df gp test1, and we're assigning it from df, again, two square brackets because we are signifying that it's a column. We're doing body style and price.
Shawn, another question for you is, can we ignore as index equal to false in a group by function?
No, we cannot ignore this because it is necessary to have that, because otherwise it'll have it indexed, and then that'll mess up our appearance of the data frame, and it'll add an indexing to the left side. So you can see in this graph, for example, we have body style and price. If we had set index to true or not set index to anything, then we would have 3, and it would look all really cramped, and it would not match the value. That's the problem.
Okay. So I guess, setting it to true or ignoring that argument would mean that you will have an extra column which represents the indexes, right?
Exactly.
Okay.
Okay. So a heat map is another way we can visualize. So a heat map is a bit of a more complex topic, but it's just showing the magnitude via color, and it's in 2 dimensions. The variation, it could be by hue or intensity, which gives us cues about how it is clustered or it varies. So using the group results, we can create a heat map, and we also have a color bar because we use plt.colorbar. And notice how we're using Seaborn and matplotlib. When we were making our regression plots, we were using Seaborn, and now we're able to use matplotlib. And you can now see why Python is so much better with its hundreds of libraries and frameworks, because it allows us to use so much more things than just the original Python. Moving on though, so we can see we have a nice color bar which represents how much data we have cramped up in one place. So the redder it is, the less data there is, and the bluer it is, the more data there is. So we can see areas like this have a lot of data, while areas like this have very little data. So this is plotting the price, again, proportional to color with respect to drive wheel and body style, since that was what our group showed in the vertical and horizontal axes, respectively. This allows us to visualize how the price is related. And this is a little bit too complex for me to go through right now because we are low on time, but it is pretty simple for the most part. It is very similar. We're just adding our text.
Shawn, if you can do this quickly. Shaunak has just wanted to ask that could you explain the box and whisker plot for body style again? And if you think you have a lot to cover, you could come back to this question later on and just rewind and just let him know at the end of the workshop.
Wait, for the heat map?
Ankit, we can take that question for sure later on, because we are running out of time. Yeah. So I'll take that question for sure.
Yes. So you can just move on, and then we can look at it later.
Okay. So I think we're gonna.
I'll be in the launch area.
Okay. This one, I think we're supposed to do together, right? Okay, I think he left, but that's fine. So now, okay, now we're doing our visualization. So, or sorry, our modeling. So our model, as it says here, is gonna.
Shawn.
Yeah.
Yeah. Please go ahead. Yeah.
So a model is going to help us understand the exact relationship between different variables and how these variables are used to predict the result. So our setup is quite simple. Our model development is going to be our raw data and some algorithm to put it into that neat and easily understandable way. So our continuous numerical variables are length, width, curb weight, engine size, horsepower, city MPG, highway MPG, wheelbase, and bore. And our categorical variables are drive wheels. So as we move into building machine learning models to automate our analysis, we want to feed that model with variables that meaningfully affect our target variable, will improve our model's prediction performance, which is what we want to do. So again, we have to use all of our operations again, since we were not affecting our original data. So we do all of our regular, and then let's come here. So now let's talk about feature engineering. Selecting a subset of features from all of the many features available is called feature engineering. A regression model is used for numerical predictions, such as predicting temperature and energy consumption. Linear regression and multiple linear regression. Linear regression 1 is an example of a data model that we will be using simple linear regression, and what we used in linear regression 1. And simple linear regression is a method to simply help us understand the relationship between two variables. They are the independent variable, or the predictor variable, which is going to be X, and the response, or the dependent variable. That's what we want to predict, and it's going to be Y. So as we saw in our regression plots, the price was on the Y, and the feature or the category was on the X. Okay, so step 1. For the model development, we need to identify X and Y. For example, car features is X and price is Y. So the result of linear regression is a linear function that predicts the response-dependent variables as a function of the predictor. So we're using X to get Y. And we're using Y, and in this case we put hat, but this is just representing what the operation is going to be, and that's going to be A plus BX. A is the intercept, which is the y-intercept, which is y when x is 0, and B is the slope. Okay. So now we are loading the modules for linear regression. So sklearn is one library we need to get, but we are not taking the whole of the library. We're just taking linear regression from it. So we're putting from that library import linear regression. And then we're simply making the linear regression object by assigning LM the linear regression. How could highway MPG help us predict car price? For this example, we want to look at how highway MPG can help us predict car price. Using simple linear regression, we will create a linear function with highway MPG as the predictor variable and the price as the response variable. So in this case, we are going to be comparing engine size and price, or rather using the engine size to get an idea on how much it has an effect on price. So we're going to first fit the linear model. So we're going to use .fit, and since we assigned LM linear regression, we're going to do LM.fit, and then we're going to put X and Y since those are the variables for engine size and price respectively. After that, we can output a prediction. So since we put Y hat, we could put Y hat equals LM.predict, and then X, since that's what we're trying to predict, and then we can put a ratio, so 0 to 5. And then we get an array out, which is our prediction. We can also get the individual value. So for example, here we are getting the intercept using lm.intercept. So now we know that our y-intercept is at negative 7,963.338. Okay, we can also do a similar operation to get our coefficient. So we can use lm.coef to get our coefficient. So we can see that our coefficient is 166.86. Okay, so we can do the same on we can do the same with other columns. So here we're making another LM, this time LM1, which is also linear regression. And we are now going to make X1 and Y1. It is the exact same process every time. But remember that since price is going to be our not an entire part, we're going to put 1. But since
Shawn, are you there? I think we are facing network issue. Hello.
Am I audible? Am I like? I can't.
Yes, you are. Yes, you
Okay.
are.
Okay, that's good. So we're using 2 here on length and 1 square bracket with price. So we do this process a lot of times because we have to get the operations done for every single one. So because remember that we want to not get biased. We want to make sure that we look at all of our data and treat them equally. So we have to do this operation on every single one, whether we like it or not, because otherwise we won't get as accurate of a prediction as we could get. So, like I was saying, when we're creating a series, you do not use more than 1 column. Data frames support as many columns as needed. That's why with data frames, we're using double square brackets, and with series, we only need 1 square bracket. For value errors, use double square brackets while defining X and Y in machine learning models. Okay, now we can start also making regression plots. This is a little something I like to call a dream regression plot. It has all of our points on the trend line which means that this will be crazy accurate. It'll be incredibly accurate because all of our dots are sticking to the trend line, which means that chances are that's going to continue. And this is a correlation between length and price, by the way, which means that length is seeming to be a very good predictor of price. Okay, we can do this a couple different times, and you can see we've done this on multiple different columns like city MPG, horsepower. And notice how some of these actually get less and less. Like bore or city MPG, the more you have, the lower the price. And again, this is probably due to the fact that if you do have more city MPG, you more than likely have a cheaper car due to fuel economy and smaller cars. And we can do this a lot of different times. In fact, we have to if we want to avoid bias. Okay, let's talk about the key learnings. First is model development equals algorithm plus data. That is what we want to follow throughout. Next is building linear regression models for predicting the price of the car. Coefficient, intercept, equation. We use .fit and .predict in order to get a prediction. And then we use a regression plot using Seaborn, such as these. Then we identified what are good predictors and bad predictors. So for example, this is a very bad predictor. Sorry, this is a very good predictor of price, even though it goes down. The reason for this is because they are sticking very tightly to that line. And you can assume that more curb weight means less price. And so remember always that just because it is going downwards doesn't mean that it is a bad predictor of price. Matter of fact, what matters is how close it is to this, to the trend line, and how vertical it is. We don't want it horizontal because horizontal signifies less predictiveness. Okay, so now we go to our next model. Our next model is multiple linear regression. This is if we want to predict car price with more than one variable. So multiple linear regression is with a lot of different variables. We still only have one y, but now we have a lot of predictor variables or a lot of x's. Similarly, we also have still y-intercept, but a lot of coefficients now of the variables. Okay, so now it starts off pretty similarly, to be fair. We start off with putting a similar way again. The only difference is that this time we are putting comma-separated text in quotes with the column name, and we're assigning it the value z for now. And then we conduct all of the same operations like linear regression, the fit, the coefficient. But notice one thing, we have a lot more values now. Of course, the intercept is the same, but notice how we have more coefficients now. We have 4 coefficients to signify four different columns. And you can see here that we not only have 4 predictor variables, we also have 4 coefficients as expected. Okay. Now we have this is a slightly bigger plot, but this is for highway MPG and price. Now, like right off the bat, it doesn't look too accurate. You can already see that there are some data points very far away from the trend line. However, you can still see that it is far from a horizontal line, and it is still a general trend of down. So you can assume that this is negatively correlated, though still correlated. Okay. Now, this is an example of a very badly correlated line. We can see that the points for, say, highway MPG are a lot closer to the generated line and on the average decrease. The points for peak RPM have more spread around the predicted line. It is much harder to determine if the points are decreasing or increasing as the highway MPG increases. So, of course, the plots are great, but we cannot be confident on whether or not the plots are perfect. So, using the method .core, we can verify this. And we can see that peak RPM, as expected due to how horizontal it is not very correlated. And then with highway MPG, we can see that it is very closely correlated in a negative direction. Okay. A good way to visualize the variance is to use a residual plot. In probability theory and statistics, variance is the expectation of the squared deviation of a random variable from its mean. Informally, it measures how far a set of numbers is spread out from their average variable. So, a residual is just the difference between the observed value, which is y, and the predicted value, which we're calling y hat. And that's called the residual, which is e. When we look at the regression plot, the residual is a distance from the data point to the fitted regression line. So that'll be, say, if this is the regression line, that would be the distance between a point and this. So that's the distance. That's going to be your residual. So a residual plot is a graph that shows the residuals on the vertical y-axis and the independent variable on the x-axis. So what we're looking at is the spread. If the points are randomly spread out, then it's more appropriate. And that sounds strange because we were just talking about why more spread is bad with regression plots. And however, when it's randomly spread out through the residuals, that means that the variance is constant, and so it's a good fit. So this plot, for example, is showing that the residuals are not very randomly spread. In fact, there's a pretty reasonably large clump here. And that leads us to believe that maybe a nonlinear model might be more appropriate for this data. We can also create a figure such as this, which is showing the actual versus the fitted values. So what this is showing is what we expected and what actually happened. And because of how close the fitted is to the actual values, we can say that our data is accurate. But of course, as it says here, there's definitely some room for improvement. Okay. Then we can do polynomial regression, also known as nonlinear regression and pipelines. So, of course, as you see the note, we need to note that this plot is short for distribution plot, and reg plot is short for regression plot. So, we can use
Shawn, you need to little fast because we need to wrap it up also in conclusion. So go a little fast.
So we can use a lot of different ways here. And so simple linear regression is first, followed by multiple and polynomial. Polynomial regression is a particular case of the general linear regression model or multiple. We can get nonlinear by squaring or setting higher order terms of the predictor variables. So we saw earlier that a linear model did not provide the best fit. So let's see if a polynomial model is going to be better. So let's skip the actual operations and go to the plot. So you can see that the polynomial fit using matplotlib for the price correlated with the highway MPG is pretty good for the most part. You can see that they are close. And you can also see that it is performing better than the linear model that we used earlier. This is because it hits more of the data points. Okay, this is just a lot of complicated math. But overall, it's trying to show the same thing, just in a mathematical sense. Okay, so this is the same chart, essentially, but we are instead now take a look at the difference. Rather than using the price from 5,000 to 45,000, we're using it from negative 20,000 to 50,000. So it is a little bit complicated, but this is the equation that we'd use for second degree polynomial. So again, from sklearn, we can import the polynomial features. Okay, and this is a lot of the similar operations, just in a polynomial way. Okay, pipeline. So data pipelines simplify the steps of processing data. We can use the module pipeline to create a pipeline, hence the name. We also can use standard scalar as a step in our pipeline. So we create the pipeline by creating a list of tuples, including the name of the model or estimator and its corresponding constructor. So here's our input. Okay, then we can input the list as an argument to the pipeline constructor. So we're putting pipe equals pipeline input, and then we're asking for our pipe, and we can see this. And now we do have to do data normalization like we did earlier, so we can perform a transform and fit this model simultaneously. So we do this in a couple different ways, like ypipe and pipe.fit. Okay, now we're at part 4. So when evaluating our models, we not only want to visualize the results, but also want a quantitative measure so we can determine the accuracy. Two very important measures here are R-squared and mean squared error. R-squared is a measure to indicate how close the data is to the fitted regression line. The value of the R-squared is the percentage of variation of the response variable that is explained by a linear model. The mean squared error measures the average of the squares of errors, that is the difference between actual value and estimated value. So here we are using lm.fit and using lm.score to find the R-squared. Now let's move on to mean squared error. So from, again, sklearn, but this time .metrics, we're importing mean squared error. So we can check the mean squared error of price and y hat, and we can get this value, which we can compare to others to get an idea of how good it is. So fitting, again, on multiple different places. Okay, now we're at part 5, prediction and decision making. So in the previous section, we trained the model using fit. Now we'll use it to predict to produce a prediction. So we need to import pyplot, and we'll also be using some functions from NumPy because we use NumPy for mathematical and scientific computation. So we create our new input, very similar. We're using some reshaping. And then we're using lmpredict, and we're using new input here. So here is our graph of new input and y hat, a pretty solid line. Okay, so now we have to decide which of these models is best. So now we have to, essentially figure out, was the simple linear regression better, the multiple linear regression, or the polynomial regression? So if it has a higher R-squared value, it's a better fit for the data. And when comparing models, the smallest MSE value is better for the data. So you want your R-squared value to be big and your MSE to be small. So for simple linear regression, we get a pretty small R-squared in comparison to the others. And we get a reasonably large MSE, in fact, larger than all of the other methods, which is exactly what we don't want. So that's already out. Now, multiple linear regression, it is good. We have a high R-squared, and we also have a small MSE. So that is going to be our maybe. Then we have polynomial fit. We have within reason, high R-squared, but we also have a very high MSE. So we want to go with multiple linear regression. So let's compare these real quick. So R-squared there's a very big difference between the R-squared of the SLR and MLR. The R-squared for the SLR is very small. Okay, and then simple linear versus polynomial. For the MSE, we can see that the polynomial fit brought down the MSE, since this one is smaller than the one from SLR. The R-squared for the polyfit is larger than the R-squared for the SLR, so the polynomial fit also brought up the R-squared quite a bit. So the MSE for the MLR is smaller than the MSE for the polynomial fit. The R-squared for the MLR is also much larger than the polynomial fit. Comparing these three models, like I said earlier, we can conclude that the multiple learning regression is the best model to be able to predict price from our data set. This result makes sense since we have 27 variables in total, and we know that more than one of those variables are potential predictors of the final car price. And that's the end. So back to you.
Hi, Shawn.
So
on. Are you waiting for Manikant?
Oh no, actually, we are now finished with this workshop.
Okay. So I guess we'll wait for. So you still have 10 minutes. You're not
Yeah,
on
I
time.
think we should wait for Mr. Roy to come because we don't know if I think he might have something to say. So we should probably
Okay,
wait.
sure. So I've tried to add him to the stream, though I don't know why, but it seems like he's dropped off again. I'll just ping him again. Oh, it seems that there is some sort of a network issue at his end. We'll leave him a message saying that
Okay.
Um, okay. So yeah. So in the meantime, I guess we can wait for questions from people if they have any.
Okay.
So hi, Manikant.
Hi, hi. Is it over? I just want to conclude. Do we have 5 minutes?
Yes. So
Thank you.
Shawn is done with his part. You still have 10 minutes, so you can take your
Yeah,
time.
yeah. Please, please. Am I on broadcast? Yeah.
You are live. Yes.
Okay, okay. So thank you so much everyone for joining this workshop. And the idea was not to tell you about the syntax and the complex mathematics, but idea was to introduce you the process, like what entire process goes into, right from getting a data to getting a decision. For in this case, we have seen not all the features are important for car pricing, right? So we wanted to introduce the process that is important. Syntax is not important because that you can learn anyway from the just a Googling from the Stack Overflow or Python documentation. The idea was once we take the data, then what goes into, we do descriptive statistics, then we go for the EDA process. That is very, very important. And when you do the then before that, in fact, data wrangling, data munging, all these steps are very, very important, right? So the idea was to go through that entire process and see, for example, what challenges do you face in missing values when there is a missing values, how to replace the missing values, then okay, how to, whether you should drop the column or whether you should not drop the column, whether you should drop the rows, and like that. Okay, and then you go for the EDA. When you do exploratory data analysis, then you come to know like how the spread of the data is there, right? Okay, when you do visualization, right, histogram or something like that, you can do. And then you realize when you are doing the model development, not all the features are important for your objective, that question that you are trying to answer through the data, right? Okay, so in this case you see that certain features are just useless, right? Whereas the important features are, for example, the body style or the front wheel or rear wheel and so on and so forth. So the idea is when we have data, right, we have to find out the important factors out of it through the EDA process. We have to clean it, we have to make it ready for analysis, because in real world data is not clean, right? We have to get our hands dirty, we have to make the data ready, then we have to apply techniques on that, right? And then we start making model to solve our problem. Okay, so when I say a model, then what I mean to say, you put data plus algorithm, you have a bunch of algorithm. For example, this was where we are predicting price, it was a numerical. What if it is a classification model? Then probably you might have applied KNN, probably you might have other advanced machine learning algorithms, okay, whether supervised or you might have gone for unsupervised. It all depends on the problem. So the point that I want to try to make here is that just try to understand the process, okay, and emphasis about the process that we need to follow in entire data analysis life cycle. Okay, and of course you will learn syntax along the way. That's it. Thank you so much. And for any question, we are very much in the launch area to take that. Is that okay, Shawn? Fine, thank you. Shawn, you want to add anything?
Yeah. Aside from that, yeah. Thank you very much for the opportunity. I'm very happy to. This is actually my first speaking at a conference, and I really am delighted to have
Yeah,
spoken at a prestigious conference.
yeah. Thank you so much to the 4C team and SciPy India team for the opportunity. Yeah.
Thank you so much, Manikant and Shawn. So that was a great, exhaustive talk about all the stuff that you've covered, and I learned a few things myself. I can really see that people were paying attention, and there was a lot of interest because we had a lot of questions as well. Uh, so I just wanted to thank you guys for coming on board, being available today. with everything happening all around the world, we decided to go remote, and I think this talk is this workshop and the people, both of you involved, you are a great example of how we can come together. So I guess not pointing out numbers, but I guess between the three of us, I think there could easily be a difference of 10 to 15 years between Shawn, me, and Manikant. Plus,
Yeah.
and not only that, I guess Shawn
Yeah.
Shawn is located right at the other end of the world. I'm in Mumbai. Shawn, can you, if you don't mind, can you share where you're from, where you're located right now?
Yeah, I'm in Houston, which is in Texas.
Correct. In Texas, USA. So Shawn is in Texas. Manikant, where are you?
I, IIT Delhi. Yeah.
IIT Delhi. Yes. So he's in Delhi. I'm in Mumbai. Shawn is in Houston, Texas. So this sort of is a great example of how this has come together, and how we could sort of get together to sort of have this great talk here, which would may not have been possible if things were going the conventional way in place, right?
Exactly.
So thank you so much for joining in. We still do have 5 minutes. So Shawn, if you wanted to revisit the question where I guess someone asked about the box and the whisker plot for body style, if you'd like to answer that now, or you'd like to take it later, that's fine. Because we had 5 minutes before we rushed off for lunch. I do understand it's late at your side of the world, but
Yeah.
if you'd like to stay on and answer it here, because I guess people are still hanging around. Otherwise,
Shawn, you can take that question.
Yeah.
Go to
Okay.
the Jupyter notebook and take that. Yeah.
Okay, so here are the. So what was the question again?
Yes, I'll read it out to you. What was that? So can you please explain the box and the whisker plot for the body style? So I guess you specified the body style somewhere. Yeah, that's
Yeah, this is the body style. So what the reason that we can assume that the body style is not a good predictor of price is because we can see that there's a lot of overlap. Like, so for example, you can see just this line right here. We have hardtop, wagon, the sedan, and even the hatchback. So that's already four right there, and that means that there's a lot of overlap. And overlap means that there's going to be a lot of going to be a lot of different data at the same place, and that's going to cause the what's it called? That's going to cause the price to not be as much so correlated as it could be if they were not if the line was not there.
okay. Got it. I hope, Shaunak, that answers your question. Just before signing off, I think Manikant has put up an exercise for all the attendees to attempt, right? And we put it up in the stage chat. We've also put it up in the chat.scipy channel. So you guys can sort of just check that exercise out and try it out if you want to. Shawn possibly could rush off because it's quite late there, but Manikant will be available. So Manikant, I guess you will be available in the chat.scipy in your workshop room. And what we can do is okay. And what you can do is you can move to the lounge area, and you can take over the lakeside room, and you can just wait there around, and you can sort of answer questions for everybody. So the lounge area, guys, attendees, the lounge area is a great place to sort of interact directly. You can actually switch on your audio and video and talk to people. And this the whole online experience, the best part is that you can directly talk to people without having to sort of physically approach them and shying away from physically approaching them. So please,
right.
Please just move to the lakeside room in the lounge area if you want to talk to Manikant, and if possibly talk to Shawn as well, right? So they will be available throughout the day as much as is possible in the chat.scipy channel and in the lounge area. Thank you so much, Manikant and Shawn, for joining us. Great talk. Have a great day.
Thank you, Ankit, for the opportunity.
And yes, and see you throughout the rest of the day and tomorrow as well. See you. Bye-bye.
Yeah, sure. We are very much there. Yeah.
Correct. Okay. So any of the attendees hanging around, just wanted to let you know that We will be signing off now for lunch. So the lunch will last from 1 p.m. to 2 p.m. and then we'll be signing in again in the LH101 stage for the next talk, which is Indic NLP, which seems to be really interesting as well. See you post lunch. Bye bye.